And probably put his chairs here somewhere. How much work? Just for one day. Got an IT problem. Get up on this chair, fall down.
Yeah. What? The guy already did what variation. I just have to do it a little more. It's really easy. Yeah. Let me see this. How you doing that for us? But it works. Yeah. Yeah. Because I'm assuming that sounds right there. Yeah. It's really drawings. Yeah, that's what I want to. This is one of the quizzes. Bro gave me a 0 just because I didn't sign it. Even though I was there in person. Okay, this is one. So, yeah, this part, and that's the bully. Did that shit. But he gave me the 0. I thought that. You about to do the same things. That's your. That is like a piece, that is like this box. That's the news up the tram.
Hey Troy, how's it going? You good?
Got some heat transfer right here.
What?
Back in sheet.
Oh, sounds good.
You know what I mean, bro? Oh, you for velocity. Yeah, to solve for the angular velocity. I didn't know, bro. I did it all for them. Oh, bro, no, I know how to do it. Yeah, but it took forever. Yeah, but I still got to do the whole thing. Like, I even have to use my ears. Yeah. My head's not that full. Bro, that what's it called the angle at first I was like, bro, like she didn't give it to her exactly. Yeah, and someone was like, oh, these autocations like no, all the equations are there. I was like, bro, I do these right now. Yeah. The first 15 minutes, she didn't give us that, so I was like trying to solve it out. Hell yeah. Yeah, probably next location. Yeah. I'm just. I have a lot. This one more. This side. I like. The new one I was like, how I tripping about much that. I really want to but. So I don't get it. It's already done. Before we even go. Yeah. We get lots of money. Can you get it from hand? You to run it or you have to lose on everything. Like the landing gear types? Yeah. And we have for. Oh, hold on. Material. Or mechanical solid.
Oh, pretzel? Oh, I'm okay. We'll save my stuff. Maybe I.
Okay.
Next.
Did you ever take the photo?
All right, it's 1 o'clock, so let's go and get started. So first of all, for those of you in the class, I apologize if you're sitting on this side of the room. I don't know what's going on with the projector. I need to call IT to fix it. So if you're sitting on this side, I guess you're gonna have a really sore neck at the end of class. You have to look at the projector on the side. If you're on this side of the room, that's fine too. So if you want to move over there, that's fine. Yeah, I don't know what's going on with this projector on this side. So okay. All right, so today is another day in heat transfer. So probably first thing everyone's probably noticed is that your midterm 2 scores are graded. Now the average on midterm 2 was almost 39 out of 50, is about 38.7. So it's going to say something different on Canvas, because remember, I have the policy in this class where I swap your midterms if you scored better on the second midterm. So if you notice on Canvas, you should have 2 midterm scores. The higher of your 2 midterms will be in the slot for midterm 1, just because that one counts for 30%. And your second midterm score will just be the lower one, but that's worth 20%. So just double check on Canvas. I kind of double check myself to make sure I did all the swapping correctly. But if I didn't swap your guys' scores, just let me know. And I have your exams to pick up for today as well. Okay. All right. Other announcements. So I will be posting homework 7 soon. So homework 7 is the last homework that you're going to be working on for this class. It's all about radiation heat exchange, and so that's what we're going to start today. So you probably won't have everything you need to finish it. Probably not until the end of the lectures for next week. Okay. But we'll start it today, and then we'll probably finish up radiation exchange by next week. I'm hoping I'm skipping a few things with the radiation just because I want to make sure we have enough time to do a review session. At the very least, for our last lecture session, I want that to be all review. But if we can make this the entire last week review, I'm going to try to aim for that. But we'll see how much we can get done the next few lectures. Okay. All right. Any questions I can answer before we get started? Yes.
So for our final, I know it's cumulative, but I assume it's gonna be majority radiated.
No, actually, so you probably expect an even split of conduction, convection, and radiation. So yeah, so the final is cumulative, but it's not going to be absolutely everything that we've covered in the class, because it's impossible to do everything in one exam. So probably sometime next week, I'll put out a study guide for the final exam, and you'll see it's a curated list of the topics that we went over in the class. So I might skip some things. I might skip some things like fins, maybe like free convection, things like that. I'll maybe take out 1 or 2 topics, from the previous midterms, just so that you're not studying absolutely everything. Yeah. Mm-hmm. Question, yes.
I'm sure my grade's gonna stay the same, but what happens if I scored the same?
If you scored the same on both midterms, then you should have the same score on both. Yeah.
That's right.
Yeah. So miraculously, actually, there was like 7 or 8 of you that did exactly the same on the first midterm. I didn't plan it that way, but you just got the same score. So I'm like, oh, that works. That works out. All right. Any other questions? Okay. All right. So let's go ahead and get started. Okay. So topic for today is radiation exchange. Okay. So I am skipping a few things in radiation. Just like I mentioned, I want to just kind of focus on just the things that you're going to use for the problems, and also just to give us time to review on the last week. Okay. Okay. I keep looking over here, but yeah, that projector is broken. Okay, so let's talk about radiation exchange. So radiation exchange, this refers to the exchange of thermal energy between surfaces through radiation. So I wanted to focus our radiation unit on this because this is probably what's as close to everything else that we've done in this class so far. Because everything else we've done in the class is, exchange of heat between different fluids, different solids, either through conduction or convection. So radiation, we're just doing kind of the same thing. Okay. Okay, so let me illustrate it for you. In fact, we've actually already done an example with radiation exchange. So this was the lecture we did right before the midterm, right? And so if you have an object here, so let's say we have a pipe, and the pipe is in some kind of enclosed room. Okay. Right. These two objects are going to exchange heat with one another. Okay. Right. So if you look back at your lecture notes, not the previous lecture, but the lecture before that, you'll see that we did this example. Right. Now, we've kind of already talked about some of the limitations of this example, but the reason we were able to analyze this example before was the fact that, the geometry here was very simple. Okay? And most notably, we have a situation where we have just a singular object completely surrounded by a room that's all at the same temperature. Okay. So really, there's nowhere for the radiation to go except to exchange with each other, essentially. Okay? Okay. Now, of course, the situation gets a lot more complicated when you add multiple objects to the situation. You have objects with a finite amount of volume, right? And so if you really wanted to analyze it in detail, you would have to analyze it from the perspective of solid angle, radiation intensity. So basically what we did on Tuesday, right? But there's a simpler way. And so if you're purely just concerned with the amount of energy that's exchanged between different objects, different surfaces, there is a simpler way to do that. And the approach that we're going to take actually is very similar to how we approach 2D conduction. Okay. Because once the geometry gets a lot more complicated, then kind of our simple formulas start to break down. Okay. But the way that we're going to approach this is we're going to use something called a view factor. Where the view factor is, you can think of it as a tabulated form of, a view factor basically summarizes some very common geometries in radiation and puts those into a table for you to analyze more easily. Okay. And so if you think back maybe about 6 weeks ago, maybe about a month and a half ago, we did something very similar. And so when we were analyzing 2D conductions, we made use of something called a shape factor, right? Okay. So I know it's been a while since we've looked at the shape factors, but you know that was kind of the idea. Where 2D conduction normally on its own is too complicated for us to analyze, at least from the heat equation. And so we use these shape factors, which were tabulated formulas or tabulated expressions for certain geometries that were very common that we can utilize for easy analysis of these heat transfer scenarios. Okay, so view factors is the same idea. It's not exactly the same approach you're going to see in a second, but it's the same concept, right? Where you know if you go from scratch, where you compute things like the solid angle and do those integrals on the hemisphere with the radiation intensity, you know that's technically the legitimate way to analyze these situations. It's just a little bit too cumbersome for many situations. Okay, so that's kind of the approach that we're going to take for this unit. For the next couple lectures, you know, we're going to look at several different examples of how to use these view factors, and you know, just so they can kind of help you out with the homeworks. Okay. All right. Any questions on this so far? Okay. All right, so let's go over some assumptions first, just because we do need to make some assumptions on certain things before we can kind of move forward with some calculations. Okay. All right, so let's talk about some of our assumptions here. Okay. All right, so the first assumption that we're going to make is that for every surface that we're analyzing, we're basically going to assume that the emissivity and the absorptivity are the same. Okay. So if you recall, you know, this again was from the lecture that we had right before the midterm, right? Every surface has certain coefficients that are used to describe how it interacts with electromagnetic waves, right? We have the emissivity, which is epsilon, right? This is a coefficient that's between 0 and 1. Right? And this is a coefficient that describes how well this surface will emit electromagnetic radiation waves. Okay. And the other one that we're going to be looking at is the absorptivity, which we gave the symbol alpha. So remember, alpha was also a coefficient that was between 0 and 1. Okay. So the absorptivity was a coefficient that described how well this surface absorbed electromagnetic magnetic waves. Now, normally these two properties for any given real surface or any given practical surface are usually going to be different. So certain surfaces are better at emitting radiation than they are absorbing it. Especially when you think about, there are a lot of surfaces that are reflective. And so, surfaces can reflect radiation pretty well. Oftentimes they can transmit radiation pretty well for any kind of translucent type of material. But for us, just to kind of keep things simple, we're going to assume that these two quantities, the emissivity and the absorptivity, are the same, right? And so basically any radiation that the surface can give out is, they have an equal ability to absorb that as well, okay? Now, there are two properties of the material that allow us to make this assumption, okay? I'm going to go over these kind of really quickly. These would make a bit more sense if we had more time to go over the stuff that I skipped. But basically, we're going to assume that our surface is diffuse. It's also gray. All right, so these are two separate properties. Oftentimes they get lumped together, kind of in an introductory heat transfer kind of class like this. But basically, these are telling these two properties basically tell us that all the radiation we're considering is independent of direction, and it's also independent of wavelength as well. So diffuse basically means that radiation is independent of direction. And then gray. Radiation is independent of wavelength. All right. So again, I'm kind of, we're kind of skipping over this discussion. So there's a lot more that we can discuss about diffuse and gray. But just to kind of describe these kind of, just very quickly, radiation, because the kind of the mechanism behind radiation is electromagnetic waves, it is, susceptible, or its properties change depending on where you are on the electromagnetic spectrum. So whether you have X-rays, infrared, ultraviolet, microwaves, right? Those are terms that, probably you guys have heard before, probably in terms of, protecting your skin from the sun. But, radiation has different properties depending on which wavelength band that you are on that spectrum, okay? So you can have different emissivities, you can have different radiation powers, different absorptivities, depending on the wavelength that you're looking at and the source of the radiation. But we're just going to ignore all of that. So we're going to ignore that, radiation is going to come out equally in every direction. That's what diffuse means. And for a gray surface, we are going to emit and absorb radiation from all wavelengths, basically, without any preference for any wavelength at all. Okay. But if you're interested, there is a lot of discussion in the lecture notes, but, for our purposes and the amount of time that we have left, I'm just going to skip it. But just know that, we're going to make this assumption that we have a diffuse and gray surface. Okay. Okay. Any questions on this so far? Okay. And that projector just quit. Okay. All right. So another assumption that we're going to make, at least for now. So we're going to lift this assumption next week when we discuss this. But for now, we're going to assume that we have black body radiation. So we kind of briefly mentioned, what it means for a surface to be a black body. And all that basically means is that a black body is a surface that is a perfect emitter of radiation and a perfect absorber of radiation. Okay. So basically that means that emissivity is going to be equal to 1.0 and absorptivity is also going to be equal to 1.0. Okay. Okay. So, this assumption here applies the previous assumption. So if you have a black body, then naturally you're going to be diffuse and gray as well. But they are separate. And so, next week when we go over this, we're going to look at cases where, maybe your emissivity isn't perfect, or maybe you have different emissivities between different surfaces in the geometry that you're considering. And that's going to affect your calculations as well. But just for today, we're going to assume perfect emission, perfect absorption. Yeah.
So pure curiosity, why exactly is it called black body?
Because when you visually, when you look at it, it's black.
Oh,
Yeah. Mhm. I think also the term comes from space applications as well. When you look at certain radiating bodies kind of in the distance from a space perspective, it looks black too. Mhm. Okay, so with those assumptions under our belt, let's start to introduce view factors. Okay, so let's define the concept of view factors, and then let's do some calculations with them as well. Okay. Okay. So if you recall from lecturing last time, right, the amount of radiation that one surface receives from another one depends very strongly on the geometry of the situation. Okay. So the situation in particular that we were looking at was, we had a little patch here, right? So we have a little, square patch. And we'll say that was emitting radiation out. And that was being caught by another surface up here, right? So we call this one A1, and this is A2. Okay. Okay. And so what we say is that, if we wanted to compute how much radiation A2 absorbs from A1, you would need to compute basically the solid angle between A2 and A1, right? And so what we did was we kind of drew this, the situation here. We say that this quantity here is the solid angle, omega. Okay. Right. And so what we say is that amount of radiation the amount of radiation that A2 absorbs from A1 was equal to Q. We'll call this Q12, which is the radiation from surface 1 to surface 2. Okay. This is equal to I times cosine of some, correction factor if the A2 was not, perfectly facing A1. Okay. Times the area A1 times the solid angle between them. Okay. Question, yes.
I have a question.
Yep.
Is it that it's like this, or is it like that, or does it even matter?
So in this case, if you assume A1, there's like a dome around A1, then for this simple case, A2 kind of rests on that dome. So if it's kind of off to the side, it is kind of slanted like that. Yeah.
Gotcha.
But that's really limiting. And so, because we have to make that assumption for this equation here, if you tilt that surface a little bit, or if you kind of, move the surface around a little bit, it complicates things tremendously.
Okay.
And so, with this situation, with this equation here, this equation is always true. But what's challenging is that, if you have two relatively complex looking surfaces, The solid angle can be very difficult to compute whenever you have any kind of geometric complexity. Well, the solid angle and the correction angle gamma there are both normally very difficult to compute in a general sense. Okay. So there's a better way to do this, at least for our purposes. And so the better way that we can do this is that, all right, we say that in engineering, right, oftentimes we're designing systems that have, similar geometrical characteristics. And so what if we take those situations and tabulate them in a way so that we can easily kind of compute the radiation heat transfer, specifically for those situations, just because they show up so common. And that's exactly kind of what we're going to do. And so we're going to look at certain kind of common situations, and then compute the view factors from there. Okay. Okay. So this question led engineers to develop something called the view factor. Okay. Okay. So view factor, we give the symbol F. Okay. And it usually has two subscripts to it. Okay. All right. So Fij, this describes the view factor from surface I to surface J.
Is that why earlier you had a Q1, 2?
Exactly.
Okay.
Yeah. Mm-hmm. So usually when you have radiation, we're going to consider each surface as a separate radiating body. And so usually what you're going to see in the example we're going to do, every surface is going to have a number or a label to them. So when we describe the radiation coming out from one surface, we have to specify the target as well. Right? Okay. And so if we kind of update our figure here, so let's say we have two surfaces here, and we're no longer constrained to that hemisphere of the solid angle from before. Okay. So we have two surfaces here, being very creative and just do them as rectangles. We call this surface I, surface J. Okay. Now we know that surface I, under our assumptions, is gonna be radiating heat in all directions, right? Right. So basically the idea with the view factor is that the view factor tells us the percentage, roughly the percentage of the radiation coming off from surface I that's going to be absorbed by surface J. Okay. Okay, and so if you want the exact definition for view factor, right? So I'm gonna throw quite a few formulas at you in a second. But this is the first formula. So the view factor Fij is equal to Qij, right? So for Qij, that's the amount of radiation heat transfer that goes specifically from surface I to surface J. Okay. This is going to be divided by the total amount of radiation emitted by surface I. And so that's equal to AI, right? So AI, that's just the surface area for surface I times EI. Okay? Where EI, that's the total emissive power of surface I. Okay? All right, so let me go ahead and label all these. So AI here, this is just the surface area. For surface I. Okay. Qij, this is the total amount of radiation that comes from surface I to surface J. Okay. And this EI here, this is the total emissive power, or the emissive spectral flux. I think we've given this a few names for surface I. Right. And so for this one, we're going to use our radiation formula for this. So this is epsilon times the Boltzmann constant times Ti to the fourth power. But we shorten it for E just for calculations. Okay. Okay. So with these view factors, and you're going to see there's a lot of really clever things we can do for the view factors. And expressions for the view factors can actually be tabulated for certain situations. We can use these expressions to compute radiation heat transfer exchange much more easily than computing solid angle and intensities and correction factors and things like that. Okay. All right. Any questions on this so far? Okay. Okay, good. All right, so that formula I think is hopefully pretty straightforward. But now the question now becomes, how do we obtain these view factors? Okay. Because what you're going to see is that a lot of the radiation problems that we're going to be doing in this class, a lot of the work is going to break down to how are you going to compute the view factors for every surface in this, in your geometry. Okay. So there's three different ways that you're going to compute view factors, and I'm going to do something a bit different. I'm going to list these in order of least desirable to most desirable. Okay. Okay. So number one, so you're only going to use this method for computing view factor if all the other methods fail, and most of the time you are going to be using this method and for any problems. Okay. So the first method for computing view factors is to look up the geometry that you have in a table and use the formula for view factors from that table. Okay. So that's pretty much similar to how we computed the shape factors from before. Okay. Now, why is this the least desirable? Well, it requires you to open up the textbook and look at a table. Right? So for example, right? So this is actually a preview of the example we're going to do a bit later in class today. Okay. So one very common situation that you're gonna see is two surfaces that are perpendicular to each other, but they're connected by a common edge. Oops. Forgot how to spell perpendicular. Okay. So for example, let's say we have two surfaces that look like this. I'm gonna give them a little thickness just to make it, just to emphasize it. Okay. Okay, so let's say that you have two surfaces that are going to be radiating heat on each other. The first surface here we'll say has a length L1. So second surface here has a length of L2. Okay. Right. So if you want the view factor between from surface 1 to surface 2, you can this is actually tabulated, so you can actually look this up in a table. Okay. So the view factor between these two surfaces is 1 plus ratio L2 of L1 minus square root of 1 plus L2 over L1 quantity square, okay, all divided by 2. Okay. Okay. So when the other two methods fail, and likely they are going to fail, for a given example, because you have to have some starting point. You can look up certain view factors for certain common situations in a table. Okay. And in particular, this one comes from table 13.1. So actually, if you look at chapter 13 in the textbook, chapter 13 is all about radiation exchange. And so it has different tables in there for different situations. But I think table 13.1 is probably the most common one. But I'll see if I can find one online that kind of has all this information too, at least for the ones you need for the homework. And I'll put that online for you guys. But for this one in particular, this is table 13.1 in textbook. Okay. All right, so if all else fails, just try to find your geometry or something similar to your geometry in a table, and you can look up a formula for the view factors for that situation there. Okay, question, yes.
I'm pretty sure, yeah, but if it were a view factor from 2 to 1, with those quantities just flip.
Exactly. Yeah. Yeah, so that's actually an important point. So when you're looking at view factors, they the direction matters. And so if you're going to look for the view factor between 2 and 1, you have to make sure you swap all these expressions on here, because they're usually not going to be the same. So F12 is usually not equal to F21. Okay. So don't make that assumption. And so, make sure you compute the view factors going one direction, because they are going to be different from each other. Okay. Any other questions on this?
We don't have to go too much into depth, but why is that true that they're not equal to each other?
We're actually going to go over in the next property. So there is a reciprocal property for view factors. It also depends on the surface area of the surfaces as well. Yeah.
Thank you.
Mm-hmm. Yeah. To quickly answer your question is that, from if L1 and L2 were different sizes, right? So let's say that we have a situation like this. We have one short surface and one really long surface, right? Right. So we call this surface 1, surface 2. And so if we think of the radiation coming off of surface 1, surface 2 is probably going to catch a lot of it because its area is really big. But if you look at the percentage of radiation coming off surface 2, probably a very small amount of that radiation is actually caught by surface 1 because it's much smaller. So it depends on the receiving area a lot for these cases. Yeah.
Thank you.
Mm-hmm. Okay.
If they were a 1-to-1 ratio, kind of like it's drawn in the first example,
Mhm.
could they be?
Yeah. So if they're identical, then yeah, the view factors between them would be the same either direction. Okay, so let's actually, so that kind of segues well into the reciprocal property. Okay, so the way that these problems usually go is that, usually you're going to look up a view factor for two surfaces in your situation using a table, and then you're going to use the reciprocal and summation properties to find all the other view factors. Okay. So even though most of the time the two view factors between two surfaces, they're usually not identical, but they are related to each other. So even though we can't have F12, F12 is not equal to F21, if you introduce the areas into this, they actually are the same, right? And so that formula there is not true, but this one is. So we have F12. If we take that and we multiply that by the area 1, okay, this is going to be equal to F21, right? So the view factor between those two surfaces, but the numbers are switched. And you're going to multiply that by area 2. Okay. So this property here is really useful because if you're able to compute the view factor, in one direction using a table, you don't have to use the same table to compute it the other view factor. So you can just use this equation to do that instead. Okay. So with this relationship right here, if you have the view factor in one direction, the other one is basically granted automatically. Okay. All right, so that's the reciprocal property. So that one's very useful. The last property that we're going to go over before we jump into an example is what's called the summation. Okay. Now the summation property, so the reciprocal property is true in every situation. For the summation property, we have to look at kind of a specific situation. So we do have to make some assumptions. Okay. So the summation property is only valid within an enclosed space. Okay. And so the summation property kind of builds off the first example that we did or the first example that I just kind of very briefly mentioned at the beginning of class today, right? That when you have an enclosed space, all the radiation, or you can say that none of the radiation can escape. So all of the radiation that comes off of one surface has to be absorbed by another surface at some point. Okay. Okay, so let's say that we have, let's say we have a box here, right? Okay. Let's label all these surfaces. So that's surface 1, surface 2, surface 3, surface 4. Okay. So we have an enclosed space, and so all these surfaces, they kind of form a bounding box around this area here, right? And so if we consider the radiation that's coming off of surface 1, right? All the radiation that's coming off surface 1 has to be absorbed either by surface 2, surface 3, or surface 4, right? Okay. There's just no other option because there's no way for that for the radiation to escape in this situation. Okay. And so with that in mind, right, we can form a relationship, or we can make an assumption of the view factors, or all the view factors that involve surface one. Okay. Okay. So with this, this basically tells us that F12 plus F13 plus F14. All right. So if we sum up all of these view factors, remember these view factors, remember what they represent. So they represent the percentage of radiation that's coming off of one surface that's being absorbed by another. Okay. So if we know ahead of time that everything that's coming off of surface one has to be absorbed by one of these three surfaces, okay, that means we know that the sum of these three view factors is going to be 1. Okay. So that's the summation property. So the summation property is for an enclosed space. If we sum up all the view factors, okay, and notice, which index we're summing over. So we're summing over the second index here. We're not summing over the first one. Okay, it has to equal 1. Okay. So that's another property that we're going to use. And this may seem limiting. So you may think that maybe not all the time that we're going to have an enclosed space, but your space doesn't have to specifically be enclosed by an explicit solid surface. You can also just draw your own control volume, and your control volume can serve as your enclosed space as well. Okay. So you can make an enclosed space out of a space that's not enclosed. And you'll see once we kind of get to the example later. Okay. All right. Any questions on the summation rule, summation property? Okay. All right. So that is number 3. The fourth one isn't really a property. At least it's not one in the textbook, but oftentimes, this is a very useful one. Number 4 is the number 4 way, or the top way. If you look at kind of the reverse order that we're doing, the most preferable way to compute a view factor is just to use common sense, or just by inspection. So I used to hate it when textbooks would do this. They say like, oh, just by inspection, this quantity is equal to this. Because I used to think I was the worst inspector in the world. So like, I don't see this at all. But the textbook makes it seem really obvious. And so, this last one here is not a required one. You can definitely compute all the view factors you need using the top 3. But sometimes, once you start to build some intuition for this, some view factors will be pretty obvious in terms of what they are. And so in those cases, you don't have to go through the whole song and dance of all the different equations or the different properties. You can just kind of say it straight out. And if it's not obvious, when you're first doing this, because you guys are all learning this for the first time, don't worry. Every time I use this, I'll kind of fully explain it, and then I think that will hopefully start to kind of build some intuition for the future. Okay. Okay, so let's do an example. So let's kind of put all this together. Let's do kind of a very simple example, and then we'll do one that's a bit more complicated from there. Okay. Okay, so let's look at a circle that's enclosed in another circle. Okay, so we're going to look at a situation like this. Okay. So we have an inner circle and an outer circle here. Okay. The exact radii actually don't really matter. And so we're going to call the inner circle, we'll call that surface 1. We'll call the outer circle surface 2. Okay. And so for this simple example here, we want to compute all of the relevant view factors between the surfaces. Okay. So we're not going to be computing any heat transfer. We're just going to be computing the view factors for this situation here. Okay. Okay. So we have 2 surfaces here, and so that means we're going to have at least 2 view factors, right? And so we're going to need to compute F12, which is the view factor that goes from surface 1 to surface 2. Okay. We're also going to need F21. Right, so that's the view factor from surface 2 to surface 1. But there's more view factors here actually as well. And so you might think, how can there be more? Well, it's actually possible for certain surfaces to radiate on itself. And so it's possible for some surfaces to emit radiation, for that radiation to not hit anything, and then for it to just come right back to its own surface. And so we also have F11 and F22. Okay. So F11 and F22, these are we call these the self view factors. And those self view factors are going to be relevant for certain situations. Okay. Okay. All right, so let's go through each one of these and let's compute their values either by inspection, by table value, or we're going to use some of the properties that we have. Okay, so let's start with F12. Actually, let's start with the self view factors. So I think those are a bit easier to start with. Okay, so let's start with F11 and let's compute what this is going to be. Okay. Now, remember we're assuming these surfaces are gray and diffuse, and so there's going to be no reflection of radiation at all, right? And so if we look at the geometry for surface 1 here is our inner circle, right? And so radiation is going to come off the circle like this, okay? Right? So it's all going to be kind of radiating outwards. Okay, so with that in mind, right, and just knowing the fact that we're not considering any reflection, so this radiation is not going to bounce off surface 2 and come back to surface 1, because of the geometry in the situation, I would make the argument here that F11 is going to be equal to 0. Okay, which means that it's impossible in this situation for surface 1 to radiate on itself. Okay. Now, there's a very important feature of the geometry for surface 1 here that where we can make this conclusion so easily, right? And it's the fact that surface 1 here is what we call a convex surface. Okay. So a convex surface is one where the curvature kind of goes away from the surface. Right? You guys know what concave convex means. But basically any surface that's convex, at least within the context of an enclosed situation, is going to be impossible to radiate on itself just because the curvature kind of comes in on itself. Okay. So this is one thing that you can look out for, and one way that you can simplify your calculations. If your surface is convex, or this is also true if your surface is flat as well. Okay. So flat is something that you're going to see a lot in our situations too. So flat surface also cannot radiate on itself. Now I know in reality, you know, there's going to be surface imperfection, surface, you know, roughness. In those situations, yes, on a micro scale, probably there's some micro self-radiation that's occurring. But, you know, for our purposes, we're going to assume all convex and flat surfaces are going to be, you know, impossible to radiate on itself. Okay. So this would be a situation where we can compute one of the view factors simply by inspection. Okay. Okay. So we didn't need any formulas for this. We just looked at the geometry and say that's convex. And so we know the self view factor in that case is going to be 0. Okay. All right. Any questions on F11? Okay. All right. So next one we're going to compute. Let's go to F12. It kind of seems like I'm skipping around a little bit, but you know, you'll see why I picked F12 in a second. Okay. Okay. So F12. So now that we already know what F11 is, we should know what F12 is because we can compute it via the summation property. Okay. All right. So since we have an enclosed space, right? And so we have, you know, we're only considering radiation between surface 1, surface 2. So this entire volume here, this entire space is enclosed by surface 2. Okay. So since we have an enclosed space, all of the view factors that are associated with surface 1 have to sum up to 1, right? And so all the summation of F1j, where j goes from 1 to 2, has to equal to 1, okay? So this means that F11 plus F12 has to equal to 1, okay? By our summation property. And since we've already computed F11 we computed in the previous step, we can go ahead and plug in for that. So we know F11 here is equal to 0. And so that tells us by our summation property that F12 is equal to, not 0, opposite of 0, is equal to 1. Okay. Any questions on how we obtain F12? Okay. All right, good. So that's 2 out of the 4 view factors out of the way. Okay, so now let's look at the all the view factors associated with surface 2. So let's do F21. So this is the view factor from surface 2 to surface 1. Okay. Okay. And so with this one, we are going to use the reciprocal property. Okay. Because what we just computed is we just computed F12. And so if we swap those indices, we know that the related view factor is related by the reciprocal property. Okay. Okay, so in other words, F21 multiplied by A2 is equal to F12 multiplied by A1. Okay. Right. Where A1, A2, we can assume that we can compute that. Assuming that we know, the radii or the diameter of these circles, maybe it's a cylinder, so we know the length of the cylinder as well. Usually the geometric properties we know, okay? And so if we solve this expression for F21, we get F21 is equal to F12 divided by or multiplied by A1 divided by A2. Okay, and again, this is assuming we know A1 and A2. Okay, good. And then last view factor here, that's the self view factor for surface 2, okay, F22. And the exact same way that we solve for F11, we can solve or I guess the same as we did in step 2 here. We can use the summation property together with F21 to solve for F22. Okay, so with the summation property, we know that F21 plus F22 is equal to 1. Okay. Now this is a little bit more complicated of a case here because F21 is not equal to 0, but we do know what F21 is. Right? So if you plug in for F21 here, we can solve for F22. And so we get is F22 is equal to 1 minus F12 times A1 divided by A2. Okay. All right. So that's kind of the general strategy that you're going to take in these types of problems. And so in these problems, you're going to start, usually you're going to start with one view factor that you can either compute by inspection, or maybe you have to use a table. And then you're going to use the reciprocal and summation properties to compute all the other view factors in the problem. Okay. So that's the general strategy with these problems. Okay. Question? Yes. Yes. Yep.
Do we always have to account for the self factor or?
You do, yes. And so, you know, once you start to view some of these problems, it'll become obvious when the self view factor is 0 or not. If you have a flat surface or convex surface, you can just say it's 0 right away. But if you have some kind of concave surface or a surface that has some kind of weird curvature, then in those cases, you know, the safe thing to assume is that it's non-zero in those cases. Okay, and then once you have the view factors, you can use the view factors to compute Q. Right? Okay, so for instance, let's say that we want to compute the radiation heat transfer from surface 2 to surface 1, right? And so in these situations, we know that Q21 here is going to be F21, okay, multiplied by A2 times E2, right? Right, and of course, if we plug in for E2 here, that's going to be F21 A2 times epsilon 2 Boltzmann constant sigma times T2 raised to the 4th power. Okay. All right, so in these problems, this is likely what you're gonna be looking for. And so a lot of the problems that we're gonna be considering is, I'm gonna ask you to compute the radiation heat transfer from one surface to another. So the way that you would do that is you'd first compute the view factor, then you multiply the view factor by the surface area of the object and its emissive power. So that's emissivity times the sigma times the surface temperature raised to the fourth power. Okay. All right, so I think I'll call it here, just because I have the exams to give back, and the next example is a little bit lengthy, so I think we'll save that for next time. Any final questions before we wrap it up for today? Okay, all right, so I got your exams today, so come up and pick them up. So remember if you look on Canvas, the grade that you have specifically for midterm 2 may not match what you got. And that's because, you scored better on midterm 2. So if you scored better on midterm 2, I swapped your grades on Canvas so that it has higher weighting than your first exam. That's it. Thanks. Any date on that last week is okay for me before you leave. Because I know you're probably taking other exams that week too. So yeah, if any day during week 16 is fine with me. Yeah, just let me know because I have to prepare the exam before you take it. Okay, yeah, sounds good. Yeah, just do that and then I'll arrange with them. Yeah. You do?